So in this video we're going to look at how to use the trigonometric identities that we've developed to simplify trigonometric expressions. So this first expression, 1 plus cotangent squared of theta over 1 minus cosecant squared of theta, we're going to look at simplifying it a couple different ways using the fundamental identities that we've developed so far. So I'm going to start by rewriting the expression. So I've got 1 plus the cotangent squared of theta over 1 minus the cosecant squared of theta. And anytime you have a sum or difference of squares, that usually smacks of Pythagorean identity. It tells you that you should be looking to see if there are any Pythagorean identities that you can use to simplify things. And the numerator, 1 plus the cotangent squared, shows up directly right here as a fundamental identity. So we can replace the numerator, 1 plus cotangent squared, with the cosecant squared. So I'm going to start by replacing the numerator with the cosecant squared, CSC squared of theta, over, and then we want to see if we can do anything with this. So when I look over here, this is the guy who's got the cosecant in it. And what I want to notice is that if I take the 1 plus the cotangent squared of theta equaling the cosecant squared of theta, that I can get a 1 minus cosecant squared from this. I can subtract the cosecant squared from both sides so that I get 1 minus the cosecant squared of theta. I'll still have a plus cotangent squared of theta sitting there, but then I can subtract this cotangent squared from both sides. So subtract cotangent squared of theta from both sides, and I get 1 minus the cosecant squared of theta is the same as the opposite of the cotangent squared. So I can replace 1 minus the cosecant squared with the opposite of the cotangent squared of theta. And then this minus can factor out in front of the fraction bar, probably a good place for it. And then what I want to remember is that the cosecant of theta is just 1 over the sine of theta. So if I have the cosecant squared, it's going to be 1 over the sine squared. So I can rewrite the cosecant squared as 1 over the sine squared of theta. And the cotangent of theta by our ratio identities is also written as the cosine of theta over the sine of theta. So I can make that substitution in the denominator. I can say, hey, this is the cosine of theta, and this is a cotangent squared, so these are all going to be squared. I need to square both sides. So cosine squared of theta divided by sine squared of theta. And both signs are in the denominator position, so they're going to equal 1. And I'm going to be left with negative 1 from the numerator over this numerator, cosine squared of theta. And 1 over the cosine of theta is the secant of theta, so 1 over the cosine squared is going to just be the secant squared. So I get negative secant squared of theta. And this is much simpler than what I began with, so I've simplified the expression about as simple as I can get it. We could have taken another approach to simplifying the expression. So another approach would have been to take the cotangents and the cosecants right at the start. And sometimes an approach is to convert everything into sines and cosines. So we could have, for example, said, hey, I have 1 plus the cotangent squared of theta over 1 minus the cosecant squared of theta. And right away I could have looked at, well, how is the cotangent defined? Cotangent of theta is cosine theta over sine theta, which means cotangent squared is going to be cosine squared over sine squared, and cosecant squared of theta is just going to be 1 over the sine squared of theta. So we could rewrite this using just sines and cosines, by going 1 plus from the numerator, and the cotangent can be replaced with cosine squared of theta over sine squared of theta. And the denominator could be rewritten as 1 minus 1 over the sine squared of theta. And we want to remember that the division bar in a ratio like this is a grouping symbol, so this numerator and this denominator are in parentheses. And I can multiply this complex ratio by sine squared of theta divided by sine squared of theta, which is equal to 1, so this is okay to do. And then I can distribute the sine squared into each of these sets of parentheses. So I get sine squared times 1 is sine squared of theta, plus the sine squared will distribute in here and cancel with the sine squared in the denominator, because sine squared divided by sine squared will be 1. 1 times cosine squared is just cosine squared of theta. All over. Distribute the sine squared into the parentheses. We get sine squared times 1 is sine squared of theta, minus sine squared times 1 over sine squared. So we're multiplying by reciprocals here, so we just get 1. And then sine squared plus cosine squared is the Pythagorean identity. It just equals 1. So I can replace the numerator with 1. And then I want to notice that I can also use the core Pythagorean identity here to get at this guy. So I've got sine squared of theta plus cosine squared of theta equaling 1. So if I subtract 1 from both sides and subtract cosine squared from both sides, I would wind up with the relationship sine squared of theta minus 1 equals the opposite of the cosine squared of theta. So that's from subtracting cosine squared from both sides, subtracting 1 from both sides, so that I get a sine squared minus 1, which means I can replace sine squared minus 1 with the opposite of the cosine squared of theta. And now I'm in the same position I was right here, and I use the fact that 1 over the cosine squared is just equal to the secant squared of theta. So a couple different approaches that utilize the core identities to simplify an expression. We'll take a look at one more. So again, I'm going to rewrite the expression that I'm working with, 1 minus the cosine squared of the opposite of theta is being divided by 1 plus the tangent squared of the opposite of theta. And so the first thing I want to do is recognize that from the symmetry identities, that the cosine of the opposite of theta is exactly the same as the cosine of theta, because the cosine function has even symmetry. So in the numerator, I can replace this opposite of theta with a theta. Get 1 minus the cosine squared of just theta by the even symmetry of the cosine function. And then I want to recognize that the tangent of the opposite of theta, because the tangent function has odd symmetry, this is equal to, by the symmetry identities, the opposite of the tangent of theta. So if I'm squaring this, that would mean I would be squaring this. But if I square a negation, it will make a positive, and I'll just have the tangent squared of theta. So I can step back over here and write this as 1 plus the tangent squared of theta. And then I want to look at my identities. Do I have a 1 plus the tangent squared? I do right here, which means I can replace that with the secant squared. So the denominator becomes the secant squared of theta. And now I want to look at the numerator, the 1 minus the cosine squared of theta separately, and say, can I get that from this Pythagorean identity? And I can by subtracting the cosine squared from both sides. In other words, if I have sine squared theta plus cosine squared theta equaling 1, if I subtract the cosine squared from both sides, I'm going to have a sine squared of theta equaling 1 minus the cosine squared of theta. So I can make a substitution. I can substitute for this the sine squared. So I'll go ahead and do that. And then we can rewrite this as a product instead of a division if we recognize that 1 over the secant. So I have a secant in the denominator here. This is no different than saying sine squared of theta times 1 over the secant squared of theta. And if I recognize that 1 over the secant is going to equal the cosine because they are reciprocals, then I recognize that this 1 over the secant squared is just going to be the cosine squared. So I can replace the 1 over the secant squared with a sine squared, and I have something that's simpler than what I started with, and that's probably as simple as we can get it, at least for right now.